Perfect. All right, so like I mentioned, we're going to do just half of 3, 4 today. Remember, what we're doing today will not be on your quiz tomorrow. Okay, tomorrow's quiz will only be over 3-1, 3-2, and 3-3. So we have a little bit more time to practice those in Math Excel. All right, so the reason we talk about division before this section is we're going to be trying now to solve large polynomials. We might have a 4th degree polynomial or a 5th degree polynomial, things that we can't factor using factoring rules that we've known from the past. So what we're going to be doing is dividing things out of our polynomials to a point where it's small enough, like a quadratic, that we're able to find all the remaining solutions. We're going to kind of build up to that first here. We're going to start by having the solutions and creating the polynomial. So this one you guys can just do in your notebook. It says we're going to find a polynomial equation of least possible degree with integer coefficients that has a greatest common factor of 1, whose roots include the numbers -1/4, 3, and 8/5. All right. Okay, so least possible degree. Greatest common factor is 1. And then we have 3 roots. That's the important information you need to get from this. Okay, so least possible degree means we're not going to make any of our roots, any of our solutions occur more than once. They're not going to have a high multiplicity. They're just going to occur one time. And that's going to make my polynomial a little bit smaller, which is nice. Greatest common factor is what you can divide out of all of your terms. So you can think of that as far as what we're doing right now as your leading coefficient, the number that's going to be in front. So leading coefficient is going to be 1. And then when we say roots, remember that means solutions or x-intercepts. So we're going to work backwards, take those roots, we're going to build the factors, and then the factors are going to create our polynomial. All right, so because I have 3 roots, I'll use p of x for my polynomial. I'm going to put 3 parentheses. And my greatest common factor is a 1, so I'm going to put that out front. That's going to give me my leading coefficient. All right, so when we were solving before, when we had like a quadratic or a cubic, ones that we could factor, if we had a factor like x minus 2, what was our solution for x? It was 2, right? We set it equal to 0. So now we're working backwards. Now we have the answer. We want to put it back into the factor. So we'll do the middle one first. If I have a solution of 3, what should that factor have been? What would you have to set equal to 0 to get 3 as a solution? X minus 3. So make sure you include that variable in all of these factors. That's going to give me that polynomial. Okay, so x minus 3, you can check it, set it equal to 0, gives you 3. Good. Okay, what, with an x, would I need to set equal to 0 to get -1/4 as a solution? Very good. 4x plus 1, because you would have to subtract 1 and divide by 4. So what's in the numerator is going to be what's in the back of your parentheses. It's going to be the opposite sign. What's in the denominator is going to be in front of your x. So you can use that same rule for this last one. What do I have to set equal to 0 to get 8/5 as a solution? To get that solution, we'd have to add 8 and divide by 5, right? So the opposite of that is multiply by 5 and subtract 8. If I set that equal to 0, I'm going to get positive 8/5. This is your polynomial in factored form. Math Excel will most likely ask for your polynomial in standard form, which means you need to FOIL now. Okay, so foiling. Pick any 2 parentheses and multiply them together. I'm just going to work from left to right. Hopefully we can do the foiling part in our head. 4x and x, 4x squared. Then my outside terms are -12x. My inside terms are 1x. That's a -11x when I put those together. And then my last terms, 1 and -3, -3. The other parentheses I'm just going to bring down. And now I need to multiply those together. I have 3 terms times 2 terms. We practiced this in the last chapter, so this is a big distribution problem. We're multiplying everything in the first parentheses times everything in the second parentheses. Because there's 3 and 2, I should expect 6 terms when I multiply this all together. All right, so I'm going to distribute 4x squared into the second parentheses. That gives me 20x to the third and negative 32x squared. Then I'm going to distribute negative 11x into the second parentheses. That gives me negative 55x squared plus 88x. And then negative 3 into the second parentheses gives me negative 15x plus 24. And now you're just going to add your like terms, and you will have your standard form. So 20x to the third, a couple x squareds, negative 32 and negative 55 give me negative 87. 88 minus 15 gives me a positive 73x. I'll put those guys together and bring down my 24. Okay. Any questions on the pieces of that? Building your factors first, and then multiplying your factors together to get the polynomial. All right, moving on. Okay. Oop, I skipped a slide. We have a theorem we need first here. All right, so we have a theorem that says if you have a root, a solution of a plus square root b, these will always come in pairs. You will also have a root of a minus square root b. These are conjugate pairs is the word that we use. Conjugate means same terms, different sign between them, 1 plus, 1 minus. It's important because you might see problems like this where they give you one of the 2 pairs, like 2 minus square root 5, and you have to know that there's another root that's missing. The reason these come in pairs are, think about this as something that we would get from like the quadratic formula when we solve a quadratic. When we have that quadratic formula, it's always something plus or minus my radical. That's why they're coming in pairs. It's always the number plus the radical and the number minus the radical when we get those solutions. All right, so example, find a polynomial with least possible degree, leading coefficient of 1, and we have these roots, 2 minus square root 5, negative 3, and if 2 minus square root 5 is a root, according to this theorem, what else is a root? Its conjugate, which is 2 plus square root 5. Okay, let's put that into a polynomial. Again, leading coefficient of 1 in my factored form. Let's start with the negative 3. That's the easiest one. If negative 3 is a solution or a root, what was the factor? X plus 3. Now, are you guys noticing your signs are opposite with these? If I have a root that's negative 3, it's an x plus 3 in the parentheses and vice versa. You can do the same thing with these radical ones. The radical ones look messy, but all you have to do is change the sign of everything. So if I want to write a factor that goes along with that 2 minus square root 5, I can write x minus 2 plus square root 5. And if you can imagine solving that, when we move both the 2 and the 5 to the other side of the equation, we would end up with the opposite signs. We would have the appropriate root. And the same thing with 2 plus square root 5. X minus 2 minus square root 5. Just change all of your signs when you put it in the factor. Make sure there's an x in each parentheses. We need a degree 3 polynomial in this case to make sure that we're going to get 3 solutions out. Okay. This is your answer in factored form. Again, we want the answer in standard form, FOILed out form. This one's a little trickier. You're going to have to multiply those 2 sets of parentheses together. Now there are 3 terms times 3 terms, so how many terms should I expect? There's going to be 9 terms here. All right, so I'm going to set up a big parentheses here. I'm going to distribute x times everything in the middle parentheses. That gives me x squared minus 2x plus x rad 5. Okay. Then negative 2 times everything in the second parentheses. That's a negative 2x, a positive 4, and a negative 2 rad 5. And then finally, negative rad 5 times everything in the second parentheses. That's a negative x rad 5, a positive 2 rad 5, and a negative, if I have negative square root 5 and positive square root 5, what do those multiply together to be? It's a negative times a positive, so it's negative. What's square root 5 times square root 5? Guys, that is not a pre-calc question that I'm asking you right now. What is square root 5 times square root 5? Square root of 25, which is 5. If you multiply a radical times itself, you just get the number underneath. You can do this. All right. Let's look at some of these terms. You should notice some things. Some things are going to cancel here if you're doing this correctly. I have a positive x rad 5 and I have a negative x rad 5. They're gone. I have a positive and a negative 2 rad 5. Those are both gone. So anything with the radical, if you're doing it right, should disappear. I am left with then x squared. I have a negative 2x and another negative 2x. That's negative 4x. And then I have a positive 4 and a negative 5, which is negative 1. If you FOIL this back out, you will end up with the quadratic that when the quadratic was solved gave you those solutions. So that's what we would put into the quadratic formula, for example, that would give me 2 plus and minus rad 5. That's where that's coming from. Now don't forget, we have that x plus 3. We need to bring it down. That's the tough part. Last part is going to be FOILing these together. If I FOIL these together, x squared times everything in the second parentheses gives me x to the third and 3x squared. Negative 4 times everything in the second parentheses gives me negative 4x squared and negative 12x. Negative 1 times everything in the second parentheses, negative 1x, negative 3. Final answer, I've got a couple sets of like terms I can put together. I'm going to end up with x cubed minus x squared minus 13x minus 3. Okay. All right. I believe you have one on your big idea worksheet now that looks similar to this, right? I'll put that back up there in a second. Okay, so here you have 3 roots that you're given. 2, 3 minus rad 2, and negative 2/3. You also have a leading coefficient of negative 2. That leading coefficient of negative 2, you're just going to distribute at the very, very end. That's going to be your absolute last step, okay? So set it up like we practiced with the parentheses for each of your factors that's associated with each root, and then start FOILing. This is going to take you a few minutes. I'll give you some time. You can work with your groups, okay? Put it in factored form and standard form. I'll come around and help if you need me. All right, let's see how you did. Let's talk it through here. Okay, so after you put the 2 parentheses with the radicals together, you guys should have this quadratic, x squared minus 6x plus 7. After you multiply these back 2 parentheses, you should have this quadratic, 3x squared minus 4x minus 4. So definitely check those 2 chunks first. Then you've got to multiply these 3 terms times these 3 terms on the purple line, which gives you these 9 terms. Combine like terms, and then distribute the negative 2 at the very end. You have a negative 6x to the 4th, 44x to the 3rd, negative 82x squared, 8x. Don't have that, maybe figure out where you went wrong. If one of those purple parentheses was wrong, that would definitely affect the rest of it after that. Hopefully, at least find where you made a mistake at. it occurred. I'll leave that up for a minute. And then the last thing we're going to do today is the rational roots theorem, which is the next slide on your paper there. We'll get to that. Any questions on this one as you're correcting it, checking it? Okay, everybody have what they need? Okay. All right, so last theorem. Do you guys remember in Algebra 2 doing anything with P's and Q's? Does that sound familiar at all? I don't know if you've done this before or not. Yes? No? Maybe? Okay, so our ultimate goal here is to be able to solve polynomials that are of a larger degree. And there's going to be a process to that. The first step in that process is making a list of possibilities. So these are not necessarily solutions that we're about to list. They are possible rational zeros. And remember, the word rational means it can be written as a fraction. So this theorem tells us if a polynomial has a solution that can be written as a fraction, it will appear somewhere in this list, okay? And this is just going to give us a starting place then that we're going to narrow down later, and I'll show you how to do that on Thursday. So how this works is we're going to make two sets of numbers to start. P's will be factors of our constant term, which is the last term that doesn't have a variable with it. Q's will be factors of the leading coefficient, the number in front. Then the possible rational zeros are all the ways that you can do a P number divided by our Q number. So we're going to put the lists together. So we'll do the first one on the left together, and then the second one on the right at the bottom you can try with your groups in a minute. So three sets of numbers, P's, Q's, and P's over Q's. P's come from the constant term. The constant term in this problem is -3. When we're listing the factors here, we don't have to worry about negatives, only positive numbers. We'll adjust at the end for any possible signs that we have to worry about. So just factors of 3. What are numbers that multiply together to get 3? 1 and 3. Those are your only options. So P's are 1 and 3. Q's come from your leading coefficient. So in this problem, that would be a 2. Factors of 2, numbers that multiply together to get 2 are 1 and 2. Okay, again, we don't have to worry about pluses and minuses there. Now we've got to figure out all the ways we can do a P divided by a Q. So you want to do this as organized as possible. What I do is I pick a P, and then I divide it by all of the Q's. And then I move on to the next P and divide it by all of the Q's. That way I don't miss anybody. So I would do 1 divided by 1, which gives me 1. Then I would do 1 over 2, which is 1/2. We're listing fractions only here, no decimals. Then I move to my next P. 3 over 1, which is 3, and 3 over 2, which is 3/2. At the end, we're going to put plus and minus in front of each of our rational numbers. And then this creates your list of possible rational zeros. So truly there are 8 possibilities here when we think about all the positive numbers and all the negative numbers that are listed. So 8 possible rational zeros, which would then, if we were going to solve this polynomial, give us a starting place to start testing numbers and dividing things out ultimately. All right, so you can imagine if these P's and Q's lists get large, that this list could potentially get large. So you might have a lot of answers for these. Go ahead with your group and try that last one on the right there. Make your list of P's, make your list of Q's, P's over Q's. If a number shows up more than once, you do not have to write it more than once. You can just put it on there one time. It's already a possibility you're good. All right? Go ahead. All right, let's see how you did. There should be 10 numbers with pluses and minuses in front of them down here. 10 distinct numbers with pluses or minuses in front of them, which gives you 20 possible rational zeros. So if you don't have 10 numbers with pluses and minuses, maybe check your list and see which one you're missing. If you have more than 10 there, it's likely one of your numbers reduces and it looks like the same as one of these. You just got something listed more than once. All right, so I'll give you a minute to check those. Check your P's, check your Q's, P's over Q's if you don't have that. Tomorrow, quiz. Quiz tomorrow is not over what we did today, just 3-1, 3-2, and 3-3. It is open notes. It is individual, and you may use a basic calculator only, and I have those if you don't have your own. Okay, so make sure you have your notes organized for at least those 3 sections ready to go for tomorrow. You can look over things tonight. You can practice those Math XLs tonight if you want to. We'll do that tomorrow, and then we'll finish up this lesson on Thursday together. Okay? Questions for me? No? All right. We'll do the cell phone lotto.